This is Sleepy Space, a slow space story to help you fall asleep. 4.5 billion years. That is how long Earth has existed. Long before oceans formed, long before continents settled into their current shapes, long before anything that could recognize itself looked up at the sky. And yet, almost everything we know about our own past fits into a sliver so small it barely registers on that scale. We've been writing history for about 5,000 years. 5,000 years of stories, records, cities, and monuments. It feels immense when you're inside it. It feels permanent. But against Earth's full timeline, it is almost nothing. If you compress the entire history of the planet into a single 24-hour day, life appears around 4 in the morning. Dinosaurs rise and fall in the afternoon. Mammals take over in the evening. Humans appear in the final second before midnight. And everything we call recorded history, every empire, every war, every scientific discovery, happens in the final fraction of that last second, which raises a question most people never seriously consider. What if we aren't actually the first? Not the first life, the first civilization. What if somewhere in those vast stretches of deep time, long before humans evolved, something else arose? Something capable of shaping its environment? Something that built, altered, and consumed energy at a scale larger than simple biology, and then vanished so completely that we now walk across its remains without ever realizing it existed. This idea sounds like science fiction, but it is not dismissed as such by science. It is a real question, one that emerges naturally when you combine two facts. The first is how short human history is. The second is how aggressively Earth erases its past. Scientists call this thought experiment the Silurian hypothesis. Not because there is evidence of an ancient civilization, and not because anyone believes one likely existed, but because it forces us to confront something uncomfortable about the geological record. Could we even detect a civilization that existed tens or hundreds of millions of years ago? If something industrial rose up on Earth long before humans, what would be left of it today? Cities do not fossilize easily. Roads crumble, metals corrode, plastics break down. Entire continents move. Ocean floors are dragged into the mantle and destroyed. Mountains rise and vanish. Sediments are buried, heated, transformed into entirely new kinds of rock. Earth is not an archive, it is a recycling machine. The vast majority of organisms that have ever lived left no fossil record at all. They lived, died, decomposed, and were absorbed back into the planet without leaving a trace. Fossils themselves are rare accidents of preservation. So if simple life struggles to leave evidence, what happens to something more complex when you give geology enough time to work? What happens to machines after 50 million years? What happens to cities after 100 million? What happens to an entire civilization after 500 million years of erosion, subduction, heat, and pressure? Do the traces vanish completely, or do they remain in forms we haven't learned how to recognize? The Silurian hypothesis isn't an argument that ancient civilizations definitely existed. Most scientists would say the odds are extremely low. But it is also not an argument that they definitely did not. It is a calibration of certainty. It reminds us that absence of evidence is not the same thing as evidence of absence, especially when the evidence has had enormous spans of time to disappear. We tend to think of the ground beneath our feet as solid and permanent, a reliable witness to deep history. But geology tells a different story. It tells us that the surface of the Earth is temporary, that it has been destroyed and rebuilt countless times. The oldest ocean floor still in existence today is only about 200 million years old. Everything older than that has already been consumed by the planet and transformed into something else. Which means that if something did exist before us, and if it left traces behind, those traces would need to survive an extraordinarily efficient planetary erasure system. They would need to avoid being subducted, eroded, buried, melted, or transformed beyond recognition. And even then, we would need to know where to look. And more importantly, we would need to know what we are looking for. To understand whether an ancient civilization could be detected at all, we first need to understand what Earth does to evidence over deep time. Because the answer may tell us as much about our own fragility as it does about anything that may have come before us. Earth is not a museum. It doesn't preserve, it transforms. And the primary engine of that transformation is a process that most of us learned about in school, but rarely think about in terms of what it means for evidence. Plate tectonics, the slow, relentless movement of Earth's outer shell. The planet's surface is broken into massive plates. These plates float on a layer of partially molten rock beneath them. They move, slowly, a few centimeters per year in most places, about the speed your fingernails grow. It doesn't sound like much, but given enough time, those centimeters add up. Continents drift apart, oceans form between them. Then those oceans close again, and the continents collide, crumpling their edges into mountain ranges. At the boundaries where plates meet, something remarkable and destructive happens. One plate slides beneath another in a process called subduction. The descending plate gets pulled down into the mantle, down where temperatures rise, where pressure increases, where rock begins to melt and merge with the deeper layers of the planet. Everything on that plate goes with it. Sediments, fossils, whatever happened to be there. All of it returns to the mantle to be recycled into new rock somewhere else. This happens continuously. The ocean floor, in particular, is constantly being created at mid-ocean ridges and destroyed at subduction zones. It's a conveyor belt, and it moves on a schedule that's geologically swift. The oldest ocean floor still in existence today is roughly 200 million years old. That's not because nothing older ever formed, it's because everything older has already been consumed, pulled down, melted, erased. 200 million years. That's our window for anything that might have happened on the ocean floor. Before that, the evidence is simply gone. Not hidden, not buried. Gone. Returned to the planetary system that created it in the first place. Continental crust survives longer. It's thicker, less dense, harder to subduct. Some continental rocks are billions of years old, but even continents aren't safe from erasure. They erode. Wind, water, ice, and chemical weathering break down rock surfaces constantly. Mountains that stand today will be flat plains given enough time. The Appalachian Mountains were once as tall as the Himalayas. Now, they're worn down, rounded, gentle. Time and weather did that. Erosion doesn't just wear things down, it buries them. Sediment washes off highlands and accumulates in lowlands. Rivers carry particles to the sea. Layers build up. A city built on a plain might be buried under meters of sediment over thousands of years. Over millions of years, those meters become kilometers. The weight of all that sediment compresses what lies beneath. Heat and pressure transform it. What was once concrete might become something that looks like ordinary sedimentary rock. What was once metal might become an oxidized smear in a layer of stone. Then there are the unconformities. Places in the rock record where time is simply missing. Erosion removes layers, then new layers form on top of the eroded surface. The result is a gap. Sometimes a small gap, sometimes enormous. There are places on Earth where the rock record jumps from stone that's 500 million years old directly to stone that's 1.5 billion years old. 1 billion years of history just absent, worn away, or never deposited in the first place. Fossils give us a sense of how severe this erasure becomes over time. We have a reasonably good fossil record for the past 50 million years or so. We can trace lineages, see evolution in action, understand which species existed when. But go back further, and the record becomes sparse. Around 300 million years ago, we still have fossils, but they're less common. The details are fuzzier. Push back to 500 million years ago, and the record thins dramatically. Not because life was less abundant, but because time has erased most of the evidence. Scientists estimate that considerably less than 1% of all species that have ever existed appear in the fossil record. Most organisms decompose completely. They return to the ecosystem without leaving a trace. Only under very specific conditions does fossilization occur. The organism has to die in the right place, usually somewhere sediment can bury it quickly. It has to avoid scavengers, avoid decay. Then it has to remain buried in conditions that allow mineralization. Then that rock has to survive erosion, subduction, and metamorphism. Then that rock has to be exposed at the surface again in a place where someone might find it. The odds are extraordinarily low. If biological organisms, which are relatively durable in the right conditions, leave so little trace, what happens to things that aren't designed to fossilize? What happens to artificial structures? Materials engineered for purposes other than geological longevity. Even the largest structures we can imagine building are temporary on geological timescales. A concrete dam, a steel bridge, a glass skyscraper. These seem permanent to us, but leave them alone for 10,000 years and they begin to crumble. Leave them for 1 million years and they're likely gone or transformed beyond recognition. Leave them for 100 million years, subjected to erosion, burial, compression, heat, tectonic forces, and they become something else entirely. Or nothing at all. The rock record is full of gaps and transformations. It's not a complete archive. It's a scattered collection of fragments. Pieces that happen to survive in places where survival was possible. Everything else is edited out by the planet's own systems. The same systems that create new crust and destroy old crust, that build mountains and wear them away, that bury and compress and heat and melt. This is what Earth does, constantly, patiently, without regard for what might be important to preserve. It recycles, it transforms, it erases. And this erasure becomes even more complete when we consider how industrial materials behave across deep time. Steel doesn't last. It seems like it should. It feels permanent when you touch it. Strong, unyielding. But steel is iron alloyed with carbon, and iron wants to return to its original state. It wants to rust. Given enough time and exposure to oxygen and water, steel corrodes. It flakes, it weakens. Eventually, it crumbles back into iron oxide, back into something that looks very much like the ore it came from. In a few thousand years, an unprotected steel beam becomes unrecognizable. In tens of thousands of years, it's gone. What remains might be a reddish stain in the sediment, a slight concentration of iron that could just as easily be explained by natural mineral deposition. Nothing that would signal human engineering. Nothing that would say this was once a bridge or a building or a machine. Concrete behaves similarly. It's made from limestone that's been heated and mixed with water and aggregates. It hardens into something durable enough to support buildings and roads. But concrete isn't immune to time. Water seeps in, freezing and thawing crack it. Chemical weathering breaks down the bonds that hold it together. Over thousands of years, concrete returns to its constituent materials. Calcium carbonate, silicates, components that look like natural rock, especially once they've been buried and compressed under layers of sediment. Plastics are more interesting. They're synthetic. They don't exist in nature. Surely they would stand out. Surely they would persist as evidence of something artificial. And for a while they do. Plastics resist biological decay. They don't rot the way organic materials do. But they're not invincible. Ultraviolet light from the sun breaks down their molecular chains. They become brittle. They fragment into smaller and smaller pieces. Eventually into particles so small they begin to behave like dust. Over geological time, even plastics degrade. The fragments get buried. Heat and pressure alter them. Chemical processes break them down further. Given tens of millions of years, they might mineralize, transform into something that resembles a hydrocarbon deposit, something that could be mistaken for a natural organic compound. The signature of their artificial origin becomes increasingly difficult to distinguish from the background noise of geological chemistry. Glass, which feels eternal, also changes. It's not actually a solid in the strict sense. It's an amorphous solid, a supercooled liquid with an extremely high viscosity. Over long periods, glass can devitrify. Crystals form within it. Its structure becomes less uniform. It becomes more susceptible to weathering. Water etches it. Minerals precipitate on its surface. Bury a glass bottle for 100,000 years, and it might survive in recognizable form. Bury it for 10 million years, and it's likely transformed into something that resembles natural silicate minerals. Even our most ambitious constructions face this inevitability. Consider Mount Rushmore. 4 presidential faces carved into granite. Granite is one of the most durable rocks on Earth's surface. It resists weathering better than most materials, but it still weathers. Geologists have modeled how long those carved faces will remain recognizable. The estimates vary, but most suggest around 7 million years before the features erode away completely. 7 million years sounds like an eternity. But it's a brief moment in Earth's history, a tiny fraction of the time available for something to have existed before us. Cities buried under sediment face even more dramatic transformation. Imagine a city buried under a kilometer of sediment over millions of years. The weight of that sediment creates pressure. Pressure generates heat. The deeper you go, the hotter it gets. At certain depths and temperatures, the materials we think of as permanent begin to behave differently. Metals oxidize and disperse. Organic materials carbonize. Concrete recrystallizes. The entire assemblage gets compressed, heated, and chemically altered until it becomes something that resembles a natural rock formation. Rare earth elements used in electronics present another challenge. These elements don't disappear, but they disperse. A smartphone contains dozens of different elements in carefully arranged configurations. But once that phone is buried and subjected to geological processes, those elements scatter. They oxidize. They bond with other compounds. They become distributed throughout the surrounding rock in concentrations that might not be distinguishable from natural mineral deposits. The fossil record itself tells us how thorough this erasure can be. Most of what we know about ancient life comes from hard parts: shells, bones, teeth, things that mineralize readily. Soft-bodied organisms rarely fossilize. We have entire periods of Earth's history where we know soft-bodied life must have been abundant, but we have almost no direct evidence of it. Just occasional imprints in fine-grained sediments, shadows of what once existed. Now consider technology. Technology is rarely designed with fossilization in mind. It's designed for function, for efficiency, for a lifespan measured in years or decades, not eons. When technology fails or is discarded, it becomes subject to the same processes that destroy everything else: corrosion, decay, burial, transformation. The very properties that make materials useful in the present make them vulnerable in deep time. There are exceptions. Gold doesn't corrode. Certain ceramics are remarkably stable, but these materials alone don't constitute evidence of civilization. A scatter of gold particles or ceramic fragments in ancient rock could have many explanations. Natural mineral deposits, meteorite impacts, volcanic processes. Without context, without associated structures, they're just chemical anomalies. Even something as massive as a dam would eventually disappear. The concrete would crack, water would erode it, sediment would bury it. Over millions of years, the entire structure would break down into components that blend with the surrounding geology. Future geologists might notice an unusual rock formation, a concentration of certain minerals. But would they recognize it as artificial? Would they even think to look? This is the challenge. Materials decay, structures erode, the earth recycles constantly, and the timescales involved are so vast that even our most durable creations become temporary. But perhaps we're looking for the wrong kind of evidence. Perhaps what endures isn't the civilization itself, but its impact on the planet's chemistry. If physical structures disappear, chemistry might remember. Atoms don't vanish. They rearrange. They bond with different partners. They get incorporated into rock. And sometimes the specific ways they arrange themselves can tell a story about what happened when that rock was forming. Carbon is particularly interesting in this regard. Carbon comes in different isotopes. Most carbon is carbon-12. A smaller amount is carbon-13. Both are stable. Both exist naturally. But the ratio between them varies depending on how that carbon got incorporated into rock or organic material. Biological processes prefer the lighter isotope. Plants, when they photosynthesize, take in more carbon-12 than carbon-13. Animals that eat plants inherit this signature. And when these organisms die and get buried and eventually become rock or fossil fuels, that isotopic signature persists. When we burn fossil fuels, we're releasing carbon that was locked away millions of years ago. And that carbon still carries its biological signature. It's depleted in carbon-13 relative to carbon, from volcanic or atmospheric sources. This creates a distinctive pattern, a spike in carbon-12 relative to carbon-13 in the geological record, something that could, theoretically, indicate widespread combustion of organic material. The challenge is distinguishing this from natural processes. Earth has experienced massive carbon releases before. Volcanic eruptions can inject enormous amounts of carbon into the atmosphere. Methane from thawing permafrost or destabilized ocean sediments can do the same. Even large-scale forest fires leave carbon signatures. So finding a carbon isotope anomaly doesn't automatically mean industrial civilization. It means something released a lot of carbon. Figuring out what requires additional context. There's a natural event in Earth's past that provides an interesting comparison: the Paleocene-Eocene thermal maximum. Around 56 million years ago, Earth's temperature spiked dramatically over a relatively short geological period. The oceans warmed, carbon isotopes shifted. The evidence suggests massive carbon release, possibly from methane hydrates on the ocean floor. It wasn't gradual, it was abrupt by geological standards, and it left a clear signature in the rock record. If an ancient civilization burned fossil fuels on a global scale, would its signature look different from the Paleocene-Eocene event? Maybe. The speed might differ. The specific isotopic ratios might vary slightly. But distinguishing natural from artificial at this scale across millions of years becomes extremely difficult, especially when we don't know what to expect from a civilization that might have used entirely different energy sources or operated on different timescales than our own. Nitrogen tells another story. Modern agriculture relies heavily on synthetic nitrogen fertilizers. We pull nitrogen from the atmosphere and fix it into compounds that plants can use. This process, done industrially, creates specific nitrogen isotope ratios that differ from natural nitrogen fixation by bacteria or lightning. A civilization that practiced intensive agriculture might leave nitrogen anomalies in ancient soils or sediments. But again, natural processes complicate interpretation. Volcanic activity, biological nitrogen fixation, ocean chemistry. All of these can create nitrogen variations. Phosphorus is similar. Agricultural runoff carries phosphorus into waterways. It accumulates in sediments. Too much phosphorus can trigger algae blooms, which then die and decompose, creating oxygen-depleted zones. These dead zones leave traces, layers of rock with specific characteristics. But dead zones also occur naturally. Upwelling ocean currents, volcanic nutrients, natural climate cycles, all can create similar conditions. Heavy metals provide another potential signature. Industrial processes concentrate metals like lead, mercury, and cadmium. Mining, smelting, and manufacturing release these metals into the environment. They settle into soils and sediments. They get incorporated into rock formations. Our own industrial age has left a clear heavy metal signature. Lead from gasoline, mercury from coal burning. These concentrations are measurably higher than pre-industrial levels. But heavy metals also come from natural sources. Volcanic eruptions release mercury. Certain types of rock naturally contain lead. Asteroid impacts can deliver heavy metals. So finding elevated metal concentrations in ancient rock doesn't automatically signal industry. It could be a volcano. It could be a meteorite. It could be a natural mineral deposit that happened to form in that location. This is the persistent problem. Chemistry preserves signals, But those signals are ambiguous. The same isotopic ratios, the same elemental concentrations, the same chemical patterns can arise from both industrial activity and natural processes. To distinguish between them, we need context. We need multiple independent lines of evidence. We need to understand the background natural variation for that time period. And we need that background to have been preserved in the geological record, which, as we've seen, is far from complete. There's also the issue of time resolution. Rock layers don't have perfect chronological precision. A layer that represents 1,000,000 years might be only a few centimeters thick. Within that layer, everything gets mixed. An industrial civilization that lasted 10,000 years would appear as a thin anomaly within a much broader time window. Bioturbation, the mixing of sediments by burrowing organisms, further blurs the signal. Worms, clams, crustaceans all dig through sediment layers, churning them together. A sharp chemical spike gets smoothed out. A brief event gets spread across a longer apparent duration. Even with ideal preservation, even with clear chemical anomalies, interpretation remains difficult. Science requires ruling out alternative explanations. And when it comes to ancient chemistry, there are often many alternative explanations. Each must be tested. Each must be evaluated against the available evidence. The bar for claiming artificial origin is high, as it should be. Yet chemistry persists in ways that physical structures don't. Isotopes don't corrode. Elemental ratios don't erode. They can be altered, diluted, or obscured, but they remain in some form. If an ancient civilization modified its environment at a large enough scale, chemical whispers might remain. These chemical whispers lead us to a more profound question. What if an ancient civilization didn't just leave traces in rock, but fundamentally altered the planet's climate? Climate doesn't just respond to chemistry. Climate is chemistry. The balance of gases in the atmosphere, the circulation of heat through oceans, the feedback loops between ice, water, and vapor. All of it governed by chemical and physical processes that leave their own kind of record. And industrial activity, by its nature, disrupts climate. It has to. Burning fuel releases energy and gases. Building cities changes surface reflectivity. Agriculture alters water cycles. The question becomes whether these disruptions persist long enough to be detectable millions of years later. We have ways of reading ancient climate. Ice cores drilled from Antarctica and Greenland preserve bubbles of ancient atmosphere. Each layer of ice represents a year of snowfall. Deeper layers are older. The bubbles trapped in that ice contain the actual air from when that snow fell. Scientists can measure the composition of that air. How much carbon dioxide, how much methane, how much of various other gases. The record goes back about 800,000 years, not nearly far enough to detect a civilization from hundreds of millions of years ago, but far enough to show us how atmospheric composition changes over time. What the ice cores reveal is variation. Carbon dioxide levels rise and fall in patterns that correspond to ice ages and warm periods. Methane follows similar rhythms. These variations are natural, driven by orbital cycles that change how much sunlight Earth receives. The Milankovitch cycles, the wobble of Earth's axis, the shape of its orbit, the tilt angle. These factors combine to create climate patterns that repeat over tens of thousands of years. But within that natural variation, there are spikes, sudden increases in greenhouse gases, Some correspond to known events, volcanic eruptions, changes in ocean circulation, the release of methane from warming tundra. These spikes happen naturally. They're part of Earth's climate system, which means if we found a similar spike in much older rock, we couldn't immediately conclude it was artificial. It might be, or it might be a volcano, or a methane release, or an orbital forcing that happened to align in an unusual way. Speed matters, though. Natural climate changes usually operate on specific timescales. Ice ages develop over thousands of years. They retreat over thousands of years. Volcanic events can cause rapid cooling, but the recovery takes time. The current warming we're experiencing is unusual precisely because of its speed. Atmospheric carbon dioxide is rising faster than it has in the entire ice core record. That speed is a signature. It suggests something beyond natural variation. An ancient industrial civilization would presumably leave a similar signature. A rapid increase in greenhouse gases, a sharp warming event. But how rapid is rapid in geological terms? A civilization that industrialized over a few centuries would create an extremely fast climate shift. But compress that into the geological record, and the time resolution might not capture the speed. What looks instantaneous in rock might actually represent thousands of years. The signal gets blurred by the limitations of how precisely we can date ancient events. Ocean acidification provides another potential marker. When carbon dioxide dissolves in seawater, it forms carbonic acid. The ocean becomes more acidic. This affects marine organisms, particularly those that build shells or skeletons from calcium carbonate. In more acidic water, these structures dissolve more easily. They become harder to build. The result is a change in marine ecosystems and a change in the types of carbonate minerals that precipitate from seawater. These changes leave traces in rock. Carbonate rocks form from the accumulation of shells and chemical precipitation. The mineralogy of these rocks reflects the ocean chemistry at the time they formed. Scientists can analyze ancient carbonates and infer past ocean pH. If they found evidence of rapid acidification followed by recovery, it might indicate a sudden carbon release. But again, distinguishing industrial from natural becomes the challenge. Massive volcanic events acidify oceans. Asteroid impacts do too. Without additional context, acidification alone isn't definitive. The Anthropocene, our current geological epoch, provides a template. We're conducting an unintentional experiment. We're burning fossil fuels at a massive scale. We're changing atmospheric composition faster than it's changed in hundreds of thousands of years. We're warming the planet, acidifying the oceans, altering ecosystems globally. All of this is leaving a signature: carbon isotopes, temperature proxies, species extinctions, chemical pollutants. Future geologists will be able to see this layer. It will be distinctive, clear, unmistakable. But will it persist? Will geologists 100 million years from now still be able to identify it? Maybe. The carbon isotope signal should last. The temperature spike should be detectable. The species extinction event should show up in the fossil record. But the details will be lost. The specific timing, the exact mechanisms, the cultural context, all eroded by time. What remains will be a thin anomaly in the rock, a chemical signature that says something unusual happened during this brief interval. How long does a climate signal persist? Millions of years, potentially. The Paleocene-Eocene thermal maximum happened 56 million years ago, and we can still detect it clearly. The Permian-Triassic extinction, the worst mass extinction in Earth's history, occurred about 250 million years ago, and its climate signature remains visible. So climate disruptions do persist. They get recorded in rock. They can be read later. But reading them requires having rock to read. It requires that the sediments from that time period were deposited, preserved, not subducted, not eroded, not so deeply buried that they transformed beyond recognition. It requires finding those rocks, knowing where to look, having the technology to analyze them precisely, and having a framework for interpreting what the data means. Natural climate variation is enormous. Earth has been much warmer than today. It's been much colder. Carbon dioxide has been higher. It's been lower. Methane has spiked naturally many times. So finding a climate anomaly doesn't automatically mean civilization. It means climate changed. The question is why? And answering why from millions of years' distance with incomplete data becomes extraordinarily difficult. Yet even if we found such anomalies, we face a deeper challenge: the incompleteness of the very record we're searching. The rock record is not a book with missing pages. It's more like scattered paragraphs from different chapters, found in random order with entire volumes absent. Geologists call these absences unconformities, places where rock layers that should exist simply don't, where the geological story jumps from one time period to another with nothing in between. Unconformities form in several ways. Sometimes erosion removes existing layers. A landscape rises due to tectonic forces. Rivers cut down through it. Wind and weather wear it away. Millions of years of accumulated sediment disappear. Then the landscape subsides. New sediment begins to accumulate on top of the eroded surface. The result is a boundary between two rock layers that represent vastly different times. The gap between them might be 10 million years. It might be 100 million. It might be more. Sometimes sediment simply never gets deposited. A region remains above sea level for extended periods. No rivers flow through it. No lakes form. No sediment accumulates. Time passes, but it leaves no record. When that region eventually does receive sediment again, there's a gap. Not because rock was removed, but because it was never there to begin with. The Great Unconformity is one of the most dramatic examples. In many locations around the world, particularly in North America, there's a boundary where very old Precambrian rock, often more than 1 billion years old, sits directly beneath much younger Cambrian rock, around 500 million years old. The gap represents roughly 1 billion years of Earth's history. An enormous span of time simply missing from the record in those locations. Other places preserve some of that interval, but no single location preserves it all completely. What happened during those missing years? We can make inferences from other locations where some record exists. We can use radiometric dating to establish timing. We can look at the rocks that do exist and try to reconstruct conditions. But for the periods with no rock at all, we're limited. We can't know what we can't see. This becomes particularly relevant when considering ancient civilizations. If a civilization rose and fell during one of these gaps, we'd have no direct way of detecting it. No rock means no fossils, no chemistry, no climate signals, just absence. An absence, as we've established, doesn't tell us much. It could mean nothing happened. Or it could mean something happened but left no trace, because the trace was never deposited or was later eroded away. Certain time periods have particularly poor preservation. The terrestrial record is generally worse than the marine record. Continents erode. Sediment gets washed into the oceans. The oceans, being lower, accumulate that sediment and preserve it more reliably. If you want a continuous geological record, you look at ocean sediments, not continental rocks. But even ocean sediments have gaps. Sea level changes. Ocean basins open and close. Subduction consumes old ocean floor. What survives is patchy. The earlier you go in Earth's history, the patchier it becomes. We have decent records for the past few 100 million years. We have reasonable records going back 500 million years to the Cambrian explosion. Before that, it becomes much more difficult. The Precambrian, which represents most of Earth's history, has a sparse and fragmentary record. Life existed. We know this from chemical signatures and occasional microfossils. But the details are fuzzy. The timeline is uncertain in many places. Large intervals are simply blank. There's a period geologists sometimes refer to as the boring billion, from about 1.8 billion years ago to 800 million years ago. The name comes from the apparent lack of major evolutionary innovation during this time. Life existed, but it seems to have been mostly stagnant. Single-celled organisms, some multicellular forms perhaps, but nothing dramatic. No obvious diversification. The rock record from this period is particularly sparse and unhelpful. We can't say with certainty whether this apparent stagnancy is real or just an artifact of poor preservation and limited sampling. How quickly could a civilization rise and fall within one of these gaps? Human civilization, from agriculture to spaceflight, took about 10,000 years. That's a tiny interval geologically. It would be invisible in most rock records. Even if the geological record had perfect time resolution, which it doesn't, a 10,000-year civilization might appear as a single, thin layer. More likely, it would appear as a slight anomaly within a layer representing a much longer time span. Something you could easily miss if you weren't looking for it specifically. Even a longer civilization, one lasting 100,000 years or 1,000,000 years, could hide in a gap. Especially if that civilization existed during a period of continental exposure when little sediment was being deposited, or during a time when the rocks that did form have since been subducted or eroded. The gaps in the geological record are not uniformly distributed. Some periods have better preservation than others. Some environments preserve better than others. Marine environments, as mentioned, generally do better than terrestrial ones. But marine environments also get subducted. The ocean floor recycles. Statistical probability comes into play here. The more gaps there are, the more opportunities for something to hide. And there are many gaps. Not in the sense that we have zero rock from certain periods, but in the sense that we have incomplete coverage. We have samples from some locations, but not others. We have marine rocks, but not terrestrial ones from the same time. We have evidence of shallow water environments, but not deep ocean. Each of these absences is a place where evidence could be hiding. The Precambrian, being so old and so poorly preserved, presents particular challenges. It represents about 88% of Earth's history. But our understanding of it is limited. We know life appeared relatively early. We know oxygen built up in the atmosphere over time. We know there were ice ages and warm periods. but the resolution is coarse. The details are missing. And within that vast expanse of time, there's room for all sorts of possibilities, most of which probably didn't happen. But we can't rule them out with certainty based solely on the absence of evidence. This leads us to consider not just when a civilization might have existed, but what form it might have taken. When we think about civilization, we tend to think about ourselves. Cities, roads, written language, technology that looks recognizable, tools we can understand. But this might be a narrow way of defining something that could take many forms. If we're asking whether something else rose before us, we need to be open to the possibility that it might not have resembled us at all. At its core, a civilization might be defined by a few key characteristics: the ability to harness energy beyond what individual organisms can produce, the ability to modify the environment deliberately and at scale, the ability to store and transmit information across generations. These don't require cities or writing or machines. They require organization, coordination, some form of collective action that exceeds simple instinct. We assume tool use is essential. Humans evolved using tools. Our intelligence co-evolved with our hands. We manipulate objects. We build things. We extend our capabilities through physical construction. But this assumes intelligence must follow our path. It assumes hands are necessary. It assumes a terrestrial environment where solid objects can be grasped and shaped. Consider dolphins and whales. They're intelligent. They have complex social structures. They communicate in sophisticated ways. They pass knowledge between generations. But they don't use tools in the way we do. They can't. They live in water. They lack hands. Their flippers are adapted for swimming, not manipulation. Yet they've survived for tens of millions of years with brain-to-body ratios that rival or exceed our own. Their intelligence took a different form. One focused on social coordination, acoustic communication, and mental mapping of vast ocean territories. Could such intelligence develop further? Could marine mammals, or something like them, develop what we'd recognize as civilization without ever building a single tool? Perhaps through biological manipulation instead of mechanical. Perhaps through cooperative hunting strategies so sophisticated they constitute technology in a different sense. Perhaps through cultural transmission of knowledge that shapes their environment in ways we wouldn't recognize as artificial. Or consider octopuses. They're intelligent in a completely alien way. Their neurons are distributed throughout their bodies, not centralized in a single brain. Each arm processes information semi-independently. They solve problems. They use tools occasionally. They demonstrate planning and memory. But they're solitary. They don't live long enough to pass knowledge to offspring. They're evolutionary dead ends in terms of cumulative culture. But what if they weren't? What if some ancient cephalopod lineage evolved longer lifespans and social structures? What kind of civilization might emerge from distributed intelligence? Then there are the eusocial insects, ants, termites, bees. Individually, they're simple. Collectively, they accomplish remarkable things. They build structures, they farm, they wage war. They adapt to changing conditions. The colony functions as a superorganism. Each individual is expendable. The collective persists. Some ant species have been farming fungi for millions of years, cutting leaves, cultivating fungus gardens, maintaining specific environmental conditions. It's agriculture. deliberate environmental modification. But we don't call it civilization because the individuals aren't intelligent in the way we recognize. But intelligence might not need to be concentrated in individuals. It might emerge from the network, from the patterns of interaction. A sufficiently complex colony could potentially develop collective intelligence that exceeds the sum of its parts. Could such a system develop language, technology, not in forms we'd recognize, but perhaps in forms appropriate to their scale and needs? Scale itself is worth considering. We assume civilization operates at roughly human scale, buildings we can walk through, tools we can hold. But biology operates across many scales. Microorganisms are individually simple but collectively powerful. They've shaped Earth's atmosphere. They've created entire rock formations. They cooperate and compete in complex ecosystems. Could microbial intelligence exist? Could bacteria collectively constitute something we'd recognize as civilization if we understood it properly? Probably not. But it challenges our assumptions about what's possible. Size could also go the other way. Imagine organisms much larger than us. Blue whales are already the largest animals ever to exist on Earth. But they're constrained by the physics of being warm-blooded in water. On land, in different atmospheric conditions with different evolutionary pressures, could something even larger develop? And would such beings perceive time differently, operate on different scales, build civilizations that look nothing like ours because their experience of the world is fundamentally different? Time scales matter too. We think of civilizations rising over thousands of years, but that's our pace. A civilization that operates much faster might burn through resources and collapse in centuries. A civilization that operates much slower might take millions of years to accomplish what we did in millennia. Both would look strange in the geological record. The fast one might be almost invisible. The slow one might be difficult to distinguish from natural evolutionary processes. Then there's the question of sustainability. Our civilization is built on consumption. We extract resources faster than they replenish. We're not in equilibrium with our environment, but a sustainable civilization might be. It might modify its environment, but in ways that reach stable states. That don't leave dramatic signatures, that blend with natural cycles. Such a civilization might be essentially invisible in the geological record, because it doesn't disrupt systems the way we do. Biological engineering versus mechanical engineering presents another divergence point. We build machines, but biology already builds remarkable structures: shells, exoskeletons, spider silk. If a civilization focused on biological manipulation instead of mechanical construction, what would it leave behind? Probably very little. Biological materials decay. They don't fossilize easily. Genetic modifications might persist in descendant species, but we'd have no way of knowing which traits were selected naturally and which were engineered. The point isn't that any of these alternative forms definitely existed. The point is that we don't know what we're looking for if we limit our imagination to human-like civilizations. Intelligence might emerge in ways we haven't conceived. It might build things we wouldn't recognize as buildings. It might harness energy through processes we'd mistake for natural. It might leave signatures so subtle or so strange that we'd never think to look for them. With this broader lens, we can examine specific periods in Earth's past where conditions might have supported such development. Earth's history isn't uniform. There have been periods of relative stability and periods of dramatic change. Times when life flourished and diversified, and times when it nearly disappeared. If we're looking for when a civilization might have emerged, certain periods stand out. Not because we have evidence, but because conditions seem like they might have been conducive. Warm climates, high oxygen levels, diverse ecosystems, the raw materials for complexity. The Carboniferous period, spanning from about 360 million to 300 million years ago, was strange by modern standards. The atmosphere contained significantly more oxygen than today. Perhaps 30% oxygen compared to our current 21%. This allowed insects and other arthropods to grow to enormous sizes. Dragonflies with wingspans nearly a meter across, millipedes longer than a human is tall, giant scorpions. The world was a different place. The extra oxygen came from plants. Vast forests of early trees had evolved bark and wood, structures rich in lignin that resisted decay. When these trees died, they didn't rot efficiently. There weren't yet fungi or bacteria capable of breaking down lignin effectively. So dead trees accumulated, layer upon layer of organic material that eventually became the coal deposits we mine today. The planet was literally building its fossil fuel reserves. It was warm, humid, swampy in many regions. Life was abundant and diverse. The first reptiles were evolving, joining the amphibians that dominated. Could intelligence have emerged here? Could something have developed beyond simple survival? The period lasted 60 million years. That's a long time for evolutionary experimentation. But there's no evidence of anything approaching human-level cognition. The fossil record shows remarkable diversity, but nothing that suggests technological capability or collective organization beyond instinct. The Permian period followed, lasting from about 300 million to 252 million years ago. It ended with the worst mass extinction Earth has ever experienced, the Permian Triassic extinction. Roughly 90% of marine species and 70% of terrestrial vertebrate species disappeared. It was catastrophic, caused, most likely, by massive volcanic eruptions in what's now Siberia. The eruptions released enormous amounts of carbon dioxide and sulfur. Climate changed rapidly. Oceans acidified. Life struggled. But before the extinction, the Permian was relatively stable. Pangaea, the supercontinent, had formed. Climate varied from interior deserts to coastal regions with more moderate conditions. Life adapted, reptiles diversified, the ancestors of mammals appeared. Therapsids. Some were large, some were small. Some showed signs of complex social behavior, parental care. Pack hunting, perhaps. The ingredients for intelligence were assembling, though there's no indication they crossed the threshold into anything we'd recognize as civilization. The early Triassic followed the extinction from about 252 to 247 million years ago. This was a recovery period, life rebuilding after near total collapse. Ecosystems were simplified, diversity was low, but evolution was rapid. Empty niches get filled quickly. New body plans emerged. Archosaurs, the group that would eventually give rise to dinosaurs and birds, began their rise. The climate was hot. Very hot. Possibly the hottest Earth has been in the past 500 million years. Adaptation meant surviving extreme heat. Could a civilization emerge in such conditions? Perhaps. Rapid evolution creates opportunity, new forms, new strategies. But the fossil record from this period, while better than the Precambrian, is still incomplete. We have snapshots, not continuous coverage. Something could potentially hide in the gaps, though again, there's no positive evidence suggesting it did. The Cretaceous period from about 145 to 66 million years ago was the age of dinosaurs. They dominated terrestrial ecosystems for tens of millions of years. Some were enormous, some were small and likely intelligent by reptile standards. Birds had evolved, flowering plants appeared and diversified. Mammals existed but remained small and mostly nocturnal. The climate was warm, sea levels were high, there was no ice at the poles. Tropical conditions extended far toward what are now temperate zones. The Cretaceous ended with another mass extinction, the asteroid impact that killed the non-avian dinosaurs. But before that, for millions of years, conditions were stable enough for complex ecosystems to develop and persist. Could dinosaurs have become intelligent? Some species, particularly the smaller theropods, had relatively large brains for their body size. They likely had complex behaviors. But intelligence sufficient for civilization requires more than just brain size. It requires the right kind of brain organization, the right evolutionary pressures, the right opportunities. The Eocene epoch from about 56 to 34 million years ago came after the dinosaurs. Mammals had diversified dramatically. Primates appeared. Early whales were evolving back into the oceans. The climate was warm, much warmer than today. Palm trees grew in Alaska. Crocodiles lived in the Arctic. The poles were ice-free. Carbon dioxide levels were higher. The Earth was in a greenhouse state. This is closer to our own time. The fossil record is better. We have more detail about what existed and when. Early primates were small, lemur-like, nothing approaching human intelligence. Early whales were transitioning from land to sea, developing the acoustic and cognitive abilities that modern cetaceans possess. But again, no evidence of civilization, just evolution proceeding. Organisms adapting, ecosystems forming and changing. Each of these periods had potential. Warm climates tend to support more life, more diversity, more opportunities for complexity. High oxygen levels, when they occurred, allowed for larger body sizes and potentially more energy for brains. Long, stable periods gave evolution time to experiment. But potential doesn't equal actualization. Just because conditions might have allowed for intelligence doesn't mean intelligence emerged. And even if it did, it doesn't mean it reached the level of civilization. The fossil record from these periods shows us what existed. Bones, shells, impressions of soft tissue occasionally, chemical signatures, climate data. But none of it points to technology. None of it suggests deliberate, large-scale environmental modification beyond what normal ecosystem engineering creates. None of it looks artificial. Which brings us to an interesting counter-argument, one that might actually weigh against the possibility of previous industrial civilizations. Fossil fuels present a paradox. They exist. We find them. Coal, oil, natural gas. They're distributed throughout Earth's geological history. Different deposits formed at different times from different source materials. But they're there, available, accessible, and that availability might actually argue against previous industrial civilizations rather than for them. Coal forms primarily from plant material. Trees, ferns, other vegetation that died and got buried in swampy, low-oxygen environments where decay was slow. over millions of years. Heat and pressure transformed that organic material, first into peat, then into lignite, then into bituminous coal. Finally, under the right conditions, into anthracite. The process takes time, millions of years, and it requires specific conditions that don't always occur. Most of Earth's coal comes from the Carboniferous period, that time of giant insects and oxygen-rich air and vast forests of trees that nothing could efficiently decompose. The dead wood piled up, got buried, became coal. There are other coal deposits from other time periods, but the Carboniferous accounts for a significant portion of the world's coal reserves. It was a unique moment in Earth's history, a window when conditions aligned perfectly for coal formation. Oil and natural gas form differently. They come primarily from marine organisms: plankton, algae, other microscopic life that lived in ancient oceans. When these organisms died, they sank. In certain environments, particularly shallow seas with low oxygen at the bottom, they accumulated in sediments. Burial, heat, and pressure transformed them over millions of years. First into kerogen, then with more heat into oil and gas. The specific conditions required are less common than you might think. Most organic material gets consumed or oxidized before it can become petroleum. The key point is this: these resources took millions of years to form, and they've been accumulating throughout much of Earth's history. We find oil deposits that formed in the Devonian over 300 million years ago. We find deposits from the Jurassic, the Cretaceous, the Paleogene, different times, different oceans, different source organisms. But the process continued. The planet kept making fossil fuels. An industrial civilization requires energy, concentrated energy, energy dense enough to power machines, smelt metals, transport goods across distances. Early human civilization relied on muscle power, wind, and water. But the Industrial Revolution happened because we learned to harness fossil fuels. Coal powered steam engines. Oil powered internal combustion engines. Natural gas powered turbines and heating systems. These fuels made industrialization possible at the scale we achieved. If a previous civilization had industrialized, it would likely have discovered and used fossil fuels too. They're accessible, they're energy dense, they're relatively easy to exploit once you understand combustion and mining. A technological species that evolved on Earth would encounter coal seams and oil deposits just as we did, and if they used them, they would have depleted whatever reserves existed at that time. But we find fossil fuel deposits throughout the geological record. We find coal from before the dinosaurs, oil from the age of dinosaurs, gas from after the dinosaurs. If a civilization had industrialized 100 million years ago, during the Cretaceous, wouldn't they have consumed the coal and oil that existed then? Wouldn't those deposits be gone? Or at least significantly depleted? The counter-argument is that new deposits continued forming. That's true. Fossil fuels don't form once and stay static. The process is ongoing, though extremely slow. Oil forming today from recently buried organic material won't be oil for millions of years. But the deposits we mine now formed over specific periods in the past, and those periods had their own existing deposits from even earlier times. A Cretaceous civilization would have had access to Carboniferous coal and Devonian oil. If they'd used it extensively, we'd see a gap, an absence of deposits from those earlier periods. We don't see that gap. The fossil fuel record seems continuous. Deposits exist from multiple time periods, This suggests they weren't consumed by anyone before us, which suggests, though it doesn't prove, that no one industrialized before us, at least not in a way that relied on fossil fuels, unless they didn't use fossil fuels. This is where the argument becomes more interesting. Maybe we're making an assumption based on our own experience. We industrialized using coal and oil because those were available and effective. But they're not the only possible energy sources. They're just the ones we happen to exploit first. Solar energy is abundant. It doesn't leave easily extractable deposits, but it's consistent and renewable. Wind energy likewise. Geothermal energy exists anywhere you can access hot rock. Tidal energy in coastal regions. Hydroelectric energy anywhere water flows downhill. Nuclear energy if you can figure out fission or fusion. All of these are potential power sources that don't rely on fossil fuels. A civilization that developed along a different technological path might never have needed coal or oil. They might have moved directly to renewable energy, or to nuclear, or to something we haven't even thought of. Biological energy systems, perhaps. Engineered organisms that produce electricity or chemical fuels. Processes that work with living systems rather than burning ancient dead ones. If such a civilization existed, it wouldn't have depleted fossil fuel reserves. Those reserves would remain untouched, waiting for the next species to discover them, which would be us. The fossil fuel paradox would disappear. The evidence would be consistent with a previous civilization that simply used different energy sources. But this raises another question. Why would a civilization skip fossil fuels? They're relatively easy to discover. Dig into certain types of rock, and you find coal. Drill in certain geological formations, and you find oil. It's not that you need advanced technology to locate them. Early humans found coal seams exposed at the surface. Oil sometimes seeps naturally from the ground. The challenge isn't finding them, it's knowing what to do with them. Maybe an alternative civilization figured out better energy sources first, before they needed fossil fuels. Maybe their evolutionary path gave them different priorities or different capabilities. Maybe their environment didn't have easily accessible coal or oil in the regions where they developed. There are scenarios. But each requires specific circumstances. Each adds assumptions. The fossil fuel paradox doesn't definitively rule out previous civilizations, but it does create tension. It's evidence that needs explaining if we want to maintain the possibility. And as we consider alternative energy sources, we need to ask what traces those might leave. If a civilization avoided fossil fuels, what traces would its energy systems leave? The answer depends entirely on what they used instead. Some energy sources leave clear signatures. Others are nearly invisible to geological detection. Understanding what's possible helps calibrate what we might look for. Nuclear fission leaves distinctive traces. When uranium undergoes fission, it splits into lighter elements. The isotopic ratios change. Natural uranium contains mostly uranium-238 with a small amount of uranium-235. The 235 is the isotope that fissions easily. If someone extracted and enriched uranium-235 for use in reactors or weapons, the remaining uranium deposits would be depleted in that isotope. The ratio would be off, measurably different from what occurs naturally. There's actually a natural precedent for this. The Oklo uranium deposit in Gabon, Africa, contains uranium with unusual isotopic ratios. Scientists investigating in the 1970s discovered that this deposit had functioned as a natural nuclear reactor about 2 billion years ago. Groundwater acted as a moderator. The uranium concentration was high enough. The geometry was right. Fission occurred naturally, sustaining itself for potentially hundreds of thousands of years. The heat boiled away water. The reaction stopped. More water seeped in. The reaction resumed. A natural on-off cycle. Oklo tells us that natural nuclear reactions can happen. It also tells us we can detect them billions of years later through isotopic analysis. If an ancient civilization used nuclear fission, and if any of their uranium deposits survive to the present, we might see similar anomalies. Depleted uranium where it shouldn't be. Unusual concentrations of fission products. Elements that decay from fission but don't normally exist in nature, like certain plutonium isotopes. But finding such evidence requires sampling. We can't analyze every uranium deposit on Earth. We sample what's accessible, what's economically relevant. If anomalous deposits exist in regions we haven't explored or in rock formations that have been subducted or eroded, we'd never see them. The absence of detected anomalies doesn't mean anomalies don't exist. It means we haven't found them in the places we've looked. Nuclear fusion would leave even less trace. Fusion combines light elements into heavier ones. The most accessible fusion fuel would be deuterium, a heavy isotope of hydrogen found in seawater. Fusing deuterium produces helium and releases energy. But extracting deuterium from the ocean wouldn't leave a detectable signature. The ocean is vast. The amount needed, even for a global civilization, would be insignificant compared to the total. And helium, the product, is inert and would simply escape into the atmosphere or space. If a civilization achieved fusion, their energy production would be essentially invisible geologically. No fuel depletion to detect, no waste products that stand out, just clean energy that leaves no trace beyond whatever they built with it. And as we've established, physical structures don't survive geological timescales well. Solar and wind energy similarly leave minimal trace. Solar panels require manufacturing, semiconductors, metals, glass. But once those materials degrade, which they will over thousands of years, there's nothing unique about them. Silicon returns to silicates, metals oxidize, the infrastructure disappears. Wind turbines likewise. Steel towers corrode, fiberglass blades break down. What remains are dispersed elements that look like natural mineral deposits. The manufacturing process might leave traces. Mining operations create disturbed geology, concentrated waste products. But mining also occurs naturally through erosion and weathering. Distinguishing artificial from natural becomes difficult without clear context. And context erodes along with everything else. Geothermal energy presents an interesting case. Tapping into Earth's internal heat requires drilling deep into hot rock, circulating fluid to extract heat. This could potentially alter local heat flow patterns, create unusual temperature gradients that persist. But natural geothermal systems already exist. Volcanoes, hot springs, mid-ocean ridges. Distinguishing artificial geothermal from natural requires knowing what the baseline should be. And baselines change as continents drift and tectonic activity shifts. Hydroelectric power requires dams or similar structures. Dams create reservoirs. They change river flow patterns. They trap sediment. A very large dam might leave a trace in the sediment record. an unusual accumulation of fine particles upstream, a sudden change in deposition patterns. But rivers change course naturally. Landslides create natural dams. Ice dams form during glacial periods. Again, the artificial has to be distinguished from the natural, and time blurs those distinctions. Biological energy systems are perhaps the most invisible. If a civilization genetically engineered organisms to produce fuel or electricity, those organisms might not survive as distinct species. Evolution would continue. The engineered traits might spread, be diluted, or be lost entirely. Even if descendant organisms retained some modified genes, we'd have no way of knowing those modifications were artificial rather than naturally selected. Genetic engineering leaves no permanent flag saying, "This was designed." The metabolic byproducts of biological energy systems would be organic compounds, things that occur naturally. Carbon dioxide from respiration, methane from anaerobic processes, oxygen from photosynthesis. Nothing that would stand out as artificial unless it occurred at impossible scales or in impossible contexts. And even then, distinguishing deliberate from accidental becomes nearly impossible. There's also the possibility of energy sources we haven't conceived. Physics allows for phenomena we haven't mastered or maybe haven't discovered. A civilization might tap into quantum effects we don't understand, might harvest energy from processes we consider impossible or impractical. Speculating about unknown unknowns is difficult, but it's worth acknowledging that our list of possible energy sources is limited by our current understanding and imagination. The pattern becomes clear. Most clean energy sources leave almost no geological trace. They don't deplete specific resources in obvious ways. They don't create unique waste products. They don't disrupt planetary chemistry at detectable scales. A sufficiently advanced civilization using renewable or advanced energy could be essentially invisible. Not because they're hiding, but because their technology doesn't leave scars. This invisibility principle extends beyond energy. It touches on the fundamental question of how evolution produces intelligence and whether such production is inevitable or contingent. Evolution doesn't have goals. It doesn't aim for intelligence or complexity or any particular outcome. It's a process of descent with modification, shaped by selection pressures, constrained by physics and chemistry, influenced by random chance. Organisms that survive long enough to reproduce pass on their traits. Those that don't. Over many generations, populations change. Sometimes they become more complex, sometimes simpler, sometimes they stay roughly the same. Intelligence is expensive. Brains consume energy. A human brain, despite being only about 2% of body weight, uses roughly 20% of the body's energy at rest. That's a significant metabolic cost. For intelligence to evolve, the benefits have to outweigh that cost. There have to be selection pressures that favor cognitive ability strongly enough to justify the expense. In human evolution, those pressures likely included social complexity, tool use, language, and the ability to plan and adapt to changing environments. Our ancestors lived in groups. They cooperated and competed. They made tools that required skill and foresight. They communicated complex ideas. All of this selected for bigger brains and better cognitive abilities. But this is one path, not the only path, not even necessarily a common path. Evolution frequently arrives at similar solutions to similar problems. This is called convergent evolution. Eyes have evolved independently dozens of times across different lineages. The camera eye of vertebrates resembles the camera eye of octopuses, but they evolved separately. Flight evolved independently in insects, pterosaurs, birds, and bats. Each used different anatomical starting points, but all arrived at wings and powered flight. When the same problem appears repeatedly, evolution often finds similar answers. Intelligence has also appeared in multiple lineages. Primates, obviously, but also corvids, birds in the crow family that use tools and solve complex problems. Parrots that demonstrate reasoning and communication abilities. Elephants with long memories and social complexity. Dolphins and whales with large brains and sophisticated behaviors. Octopuses with problem-solving abilities despite being mollusks. Intelligence isn't unique to one branch of the tree of life. It emerges wherever the right conditions and pressures exist. But human-level intelligence, the kind that builds civilizations, appears only once in Earth's history. That might be significant. It might suggest that while basic intelligence evolves readily, the specific kind of abstract reasoning and cumulative culture that humans possess is much rarer, harder to achieve, dependent on a narrow set of circumstances. The paleontologist Stephen Jay Gould argued that if you could rewind Earth's history and let evolution play out again, you'd get a completely different result. The specific species we see today are products of contingency, random events, lucky breaks, unlucky extinctions. If a different asteroid had hit at a different time, if a different volcanic eruption had occurred, if ocean currents had shifted differently, the entire trajectory of life would change. Intelligence might never evolve, or it might evolve differently, or it might evolve multiple times in forms we wouldn't recognize. The rare Earth hypothesis takes this further. It argues that complex life, and especially intelligent life, might be extraordinarily rare in the universe. That Earth-specific circumstances, its distance from the Sun, its large moons stabilizing its axis, its magnetic field protecting it from radiation, its plate tectonics recycling nutrients, all of these had to align just right. Change any one factor and maybe intelligence never happens. But the Copernican principle argues the opposite. It suggests we're not special, that Earth isn't unique, that what happened here could happen elsewhere, that intelligence, once you have life and enough time, might be inevitable. Not guaranteed, but likely enough that we shouldn't be surprised it happened at least once. Time is a factor. Life appeared on Earth relatively quickly after the planet cooled enough to support it, within a few 100 million years. Intelligence took much longer. Life existed for roughly 3.5 billion years before anything resembling complex cognition evolved. That's a long wait. It might suggest intelligence is difficult to achieve, or it might suggest that certain preconditions had to develop first. Oxygen in the atmosphere, multicellular organisms, predation creating arms races. Each of these took time. Environmental pressures matter. Intelligence evolves when it provides an advantage. In stable, predictable environments, simple behaviors work fine. In changing, unpredictable environments, adaptability becomes valuable. The ability to learn, to modify behavior, to solve novel problems. This is where intelligence shines. Humans evolved during a period of climate instability. Ice ages coming and going, environments shifting, resources unpredictable. Adaptability was survival. But intelligence comes with trade-offs. Large brains require long development times. Human infants are helpless for years. That requires social structures that support extended childcare. It requires stable food supplies. It requires communication and cooperation. All of these things had to be in place for human intelligence to evolve. Remove anyone and the evolutionary trajectory might stall or diverge. There's also the question of whether intelligence leads to civilization. Dolphins are intelligent. They don't build cities. Octopuses are intelligent. They live short lives and don't form societies. Elephants are intelligent. They have culture and memory and social bonds, but they haven't developed technology. Intelligence alone isn't sufficient. You need the right kind of intelligence, the right anatomical features. Hands help. Long lifespans help. Social structures help. The ability to manipulate the environment physically. If intelligence is rare and contingent, if it depends on specific circumstances that might not repeat, then previous civilizations become less likely. Not impossible, but improbable. The odds that the right conditions aligned more than once in Earth's history decrease. But if intelligence is more inevitable, if it emerges reliably given enough time and diversity, then the possibility increases. Multiple shots on goal over billions of years might produce multiple results. We don't know which view is correct. We have a sample size of one planet, one history, one emergence of technological civilization. From that, we can't calculate probabilities reliably. We can observe that intelligence exists in multiple forms across different lineages. We can note that it took a very long time to reach human levels. We can acknowledge that specific circumstances were necessary, but whether those circumstances are common or rare remains an open question. These evolutionary considerations become more complex when we examine specific anomalies in the fossil record. The geological record contains mysteries, events that happened but that we don't fully understand, patterns that seem unusual, chemical signatures that don't have obvious explanations. These anomalies don't necessarily point to ancient civilizations, but they remind us that Earth's history contains surprises, that our understanding is incomplete, that there are things we haven't figured out yet. The Cambrian explosion is perhaps the most famous example. Around 540 million years ago, life diversified rapidly. The fossil record shows a sudden appearance of complex body plans, hard shells, segmented bodies, eyes, predators and prey in arms races. Before this period, life was mostly simple. Soft-bodied organisms, microbes, some multicellular forms, but nothing elaborate. Then, relatively quickly in geological terms, complexity bloomed. The word explosion makes it sound instantaneous. It wasn't. The diversification took millions of years, but millions of years is brief compared to the billions of years that came before. The question is, why? Why did complexity suddenly become advantageous? What changed? There are theories. Rising oxygen levels, evolutionary innovations in development, ecological feedback loops, predation pressure, possibly all of these together, but we don't have a complete answer. The Cambrian explosion remains somewhat mysterious. Could it have been triggered by something artificial? Almost certainly not. The fossil record shows a gradual build-up before the explosion. Precursor organisms, early experiments with body plans. It looks like natural evolution accelerating under new conditions. Nothing about it suggests intervention or artificial manipulation. But it does demonstrate that Earth's history contains rapid changes we're still working to explain. Tectonic puzzles also exist. Certain mineral distributions don't quite make sense given our understanding of plate movements. Unusual rock formations in unexpected locations, isotopic ratios that seem anomalous until you dig deeper and find a natural explanation. Each of these requires investigation. Most turn out to have geological explanations, unusual weathering patterns, ancient river systems, meteorite impacts, volcanic processes we hadn't considered. The Great Oxidation Event is another dramatic example, though this one we understand fairly well. Around 2.5 billion years ago, oxygen levels in Earth's atmosphere increased dramatically. Before this, the atmosphere contained almost no free oxygen. Life existed, but it was mostly anaerobic. Then cyanobacteria evolved photosynthesis. They began producing oxygen as a waste product. At first, the oxygen reacted with iron dissolved in the oceans, creating the banded iron formations we see in ancient rocks. Red layers of oxidized iron. But eventually, the oxygen saturated the oceans and began accumulating in the atmosphere. This transformed the planet. Oxygen was toxic to most existing life. It caused a mass extinction of anaerobic organisms, but it also enabled new forms of life. Aerobic organisms that could use oxygen for metabolism, more efficient energy production. Eventually, complex multicellular life. The Great Oxidation Event was life engineering its own environment, not deliberately, not with intention, but effectively. Organisms changed the planet's chemistry so fundamentally that it altered the trajectory of all subsequent evolution. This demonstrates that planetary-scale environmental modification doesn't require civilization. Biology alone can do it. The question becomes whether we could distinguish deliberate modification from accidental. If an ancient civilization had engineered its environment, would the signature look different from what cyanobacteria did? Maybe, maybe not. Intent doesn't necessarily leave a chemical flag. There are specific isotopic anomalies that occasionally puzzle geochemists. Unusual concentrations of certain elements, ratios that don't quite match models. Most of these get resolved with additional sampling or refined understanding of processes. Sometimes an unexpected volcanic event explains it. Sometimes a localized depositional environment. Sometimes a measurement error. But in the moment before resolution, each anomaly represents unknown territory. Out-of-place fossils occasionally make headlines. A fossil that seems too old or too young for its supposed location. Usually these turn out to be misdated or misidentified. Radiometric dating has uncertainties. Fossils can be reworked, eroded from older layers and redeposited in younger ones. What looks like an anomaly often isn't once proper context is established. But the initial discovery creates excitement. The possibility that something fundamental about our understanding might be wrong. Occam's razor applies here. When confronted with an unexplained observation, the simplest explanation that fits the facts is usually correct. An unusual isotopic ratio is more likely the result of an unrecognized natural process than evidence of ancient technology. A puzzling rock formation is more likely the product of erosion or tectonics than artificial construction. This isn't closed-mindedness, it's scientific caution. Extraordinary claims require extraordinary evidence. But Occam's razor doesn't mean mysteries don't exist. It means we should exhaust natural explanations before invoking artificial ones. and the history of science shows that mysteries do get solved. Continental drift was once mysterious. Now we understand plate tectonics. The extinction of the dinosaurs was mysterious. Now we know about the asteroid impact. Banded iron formations were mysterious. Now we understand oxygen and ocean chemistry. Some mysteries remain unsolved longer. The origin of life itself is still debated. We know it happened. We know approximately when. But the specific chemical steps from non-living chemistry to self-replicating organisms remain unclear. That doesn't mean life was designed or artificial. It means we haven't figured out the mechanism yet. Science is comfortable with "we don't know" as a temporary state. The difference between unexplained and evidence is crucial. Unexplained means we don't currently understand something. Evidence means data points toward a specific conclusion. Ancient civilizations would require evidence, not just unexplained phenomena. We'd need multiple independent lines of data converging on the same conclusion. Chemistry, fossils, structures, patterns that couldn't be explained naturally. We don't have that. We have a clean record that looks entirely consistent with natural processes, which doesn't mean the question isn't worth asking. But it does mean the answer, based on current evidence, seems to be that we're not finding traces of previous civilizations. Not because we know they didn't exist with certainty, but because nothing we've found requires that explanation. Understanding these anomalies properly requires us to consider how we'd actually conduct this investigation. If we wanted to actually look for evidence of ancient civilizations, how would we do it? Not as speculation or thought experiment, but as rigorous science. What specific methods would we use? What data would we collect? Where would we look? These aren't abstract questions. They have concrete answers, and some of this work is already happening, though not specifically aimed at finding ancient civilizations. High-resolution geological sampling would be essential. The rock record exists, but we've only examined tiny portions of it in detail. Most geological surveys focus on economically relevant formations, places where we might find oil, minerals, or other resources, or on regions that are easily accessible, outcrops near roads, coastlines, areas with active research stations, vast stretches of continental interior, and most of the ocean floor remain poorly sampled at fine scales. To detect brief anomalies, you need continuous sampling across geological boundaries. Core samples that capture transitions between different time periods. Sediment cores from ocean basins that preserve long stretches of time without gaps. Ice cores, which we already use for recent climate history, go back nearly 1 million years. Extending similar techniques to older deposits would help, though ice obviously doesn't survive from millions of years ago. Ocean sediments and lake beds become the analogues. Isotopic analysis would be crucial, looking for chemical signatures that indicate rapid environmental change or unusual element distributions. Carbon isotopes to detect large-scale combustion or biological anomalies. Nitrogen and phosphorus to identify agricultural signatures. Heavy metals that might indicate industrial processes. Uranium isotope ratios to check for nuclear activity. Each of these requires precise measurement and comparison against natural baselines. The challenge is establishing what's natural. You can't identify an anomaly without knowing what normal looks like. And normal varies depending on location, time period, and environmental conditions. A spike in carbon might be volcanic, or it might be a methane release, or it might be forest fires. Distinguishing these requires context, associated minerals, depositional environment, other chemical markers that narrow the possibilities. Statistical analysis becomes important. One anomaly might be chance, two might be coincidence. But patterns across multiple independent samples become more interesting. If you found the same unusual signature at the same time boundary in cores from different continents and ocean basins, that would suggest a global event, something that affected the entire planet simultaneously. That's the kind of pattern that demands explanation. Deep ocean sediment cores are particularly valuable. Ocean basins accumulate sediment continuously. Unlike continents which experience erosion and non-deposition, the deep ocean receives a steady rain of particles, dead plankton, dust, dissolved minerals precipitating out. This creates relatively complete records, though even these have limitations. Bioturbation mixes the layers, currents can disturb sediment, and, of course, old ocean floor gets subducted, so there's still a time limit. Searching for synthetic molecules offers another approach. Modern plastics are synthetic polymers that don't occur naturally. If they survived in some altered form, they might be distinguishable from natural organic compounds. Their molecular structure, even if partially degraded, might retain signatures of artificial origin. Similarly, certain industrial chemicals, pesticides or pharmaceuticals, might leave traces. But this assumes such molecules can survive geological timescales, which is uncertain. Urban geology presents an interesting concept. Cities concentrate materials: metals, concrete, glass, asphalt. If a city were buried and compressed over millions of years, would it create a distinctive layer? A concentration of elements that doesn't match surrounding geology? Possibly. But identifying such a layer requires knowing where to look. Ancient cities wouldn't be where modern cities are. Continents drift. Coastlines change. A city from 100 million years ago could be anywhere, if it existed at all. Computational modeling helps set expectations. Scientists have modeled what our own civilization would look like in the geological record. If humanity disappeared today, what would remain in 50 million years? The answer is surprisingly little. Most structures would be gone, metals corroded, concrete weathered, cities buried and compressed into thin layers. The main signatures would be chemical: carbon isotopes from fossil fuel burning, plastics degraded into hydrocarbons, heavy metals in sediments, species extinctions visible in the fossil record. It wouldn't look obviously artificial to future geologists without considerable analysis. This modeling tells us what to look for and how hard it would be to find. It calibrates our expectations. If our own relatively advanced civilization leaves such subtle traces, what could we realistically expect from something older? Probably even less. The further back you go, the more erosion and geological processing has occurred. The harder detection becomes. The scientific method demands null results be taken seriously. If you search rigorously and find nothing, that's information. It doesn't prove absence, but it constrains possibilities. If extensive sampling of geological boundaries shows no anomalies that require artificial explanation, that's meaningful. It suggests either nothing was there, or it's hidden below our detection limits, or it's in places we haven't sampled yet. Some of this research is already happening, though for different reasons. Climate scientists study past climate changes to understand natural variability and improve future predictions. Geochemists analyze isotopes to understand Earth's chemical evolution. Paleontologists examine extinction events to learn about ecosystem dynamics. None of them are specifically looking for ancient civilizations, but the data they collect would reveal anomalies if they existed. The absence of such discoveries in decades of research is itself suggestive. Of course, absence of evidence in explored areas doesn't equal evidence of absence everywhere. The Earth is large. The geological record is incomplete. Sampling is limited. There could be regions, time periods, or signatures we haven't examined adequately. This is why the question remains open despite no positive evidence. Science can't prove a negative with absolute certainty. It can only say what the data shows and doesn't show. This methodical approach leads us to our final consideration: what this question reveals about humanity itself. The question of whether we're Earth's first civilization isn't really about the past. It's about perspective, about how we see ourselves, about what we think matters and what endures. It forces us to look at our moment in time differently, to recognize both how brief it is and how consequential it might be. Deep time is difficult for human minds to grasp. We evolved to think in lifetimes, generations at most. Our brains handle decades reasonably well, centuries with effort, but millions of years? Billions? These numbers become abstract. They lose meaning. We say them, but we don't feel them. The scale is too large, the duration too vast. Yet that vast duration is real. Earth has been here for 4.5 billion years. Life has existed for nearly 4 billion. Complex multicellular life for over 500 million. Humans in our current form for maybe 300,000 years. Recorded history for 5,000. Industrial civilization for about 250. Our entire story, everything we've built and discovered and created, occupies the thinnest sliver of Earth's timeline. A moment, a blink. This perspective brings humility. We're not the culmination of Earth's history. We're a current chapter, one experiment among countless others. Life has been trying different approaches for billions of years. Most went extinct, some persisted. A few, including our lineage, developed complexity and intelligence. But there's no guarantee we're permanent. No assurance we'll last. Earth will continue with or without us. Our civilization feels solid, permanent. We've built cities that seem like they'll stand forever, created technologies that feel fundamental to existence. But geology teaches otherwise. Everything we've made is temporary. Given enough time, it will erode, decay, transform, disappear. The pyramids won't last 100 million years. Neither will our dams or roads or satellites. The planet will recycle it all eventually. Turn it back into rock and sediment and maybe, eventually, new life forms that have no idea we existed. This impermanence matters for how we think about the future. We're making decisions now that have long-term consequences. Climate change, nuclear waste, species extinctions. These impacts will outlast any individual human lifespan. They'll affect generations we'll never meet. But even these long-term problems are short-term on geological scales. Climate will eventually restabilize. Radiation will decay. New species will evolve. Earth is resilient over deep time, even if individual ecosystems and species are not. But that's cold comfort. We live in the present. Our children and their children live in the near future. What happens over the next few centuries matters immensely to human well-being, even if it's insignificant to geology. The question isn't whether Earth will be fine eventually. It's whether we'll be fine, whether the systems we depend on will remain stable enough to support civilization. The Anthropocene, our current geological epoch, might be brief. A thin layer in future rock, carbon isotope anomalies, plastics in sediments, heavy metals, mass extinction signature. Future geologists, if any exist, might detect it easily, or they might miss it. Depends on how long we last and how dramatically we alter the planet. If we stabilize quickly, transition to sustainable systems, avoid catastrophic disruptions, our signature might be subtle. A brief spike and recovery. If we don't, it might be more dramatic. A clear boundary marking major change. Either way, we're leaving traces. Deliberately or not, we're modifying Earth's chemistry and biology at scales that will persist. This is both sobering and clarifying. It means what we do matters. Not in some cosmic, eternal sense, but in the practical sense that we're affecting the planet's trajectory. We're part of Earth's story now. A chapter that will be readable, even if brief, to anyone who looks closely enough. If we're not first, if something came before us, then we're part of a pattern. Intelligence emerging, building, perhaps ending, then the planet continuing. If we are first, the responsibility feels different, heavier somehow. We're the first part of Earth to become aware of Earth's history, to understand geology and evolution and deep time, to recognize our place in the vast sweep of planetary change. That awareness comes with responsibility, not to the planet, which will endure regardless, but to ourselves and to the potential for continued intelligence and complexity. The value of this question isn't really about finding ancient ruins or detecting chemical anomalies. It's about the perspective it provides, looking at Earth's timeline and seeing our moment within it, recognizing that what seems permanent is temporary, that what feels significant might be brief, that we're part of something much larger and older than ourselves. This doesn't make our actions meaningless. If anything, it makes them more meaningful. Precisely because our time is limited, what we do with it matters. The choices we make now shape the trajectory of the only civilization we know exists. We're Earth's current experiment with technological intelligence. How long that experiment runs depends partly on luck and partly on wisdom, on whether we can learn to live sustainably within Earth's systems rather than disrupting them beyond recovery. Science is a tool for gaining perspective, not just about the world, but about ourselves. The Silurian hypothesis, the question of ancient civilizations, the investigation of deep time, all of these help us see more clearly. They strip away the assumption that we're central or permanent. They place us in context, and context, properly understood, is liberating. It shows us both how small we are and how much potential we have, how brief our moment is, and how much we can affect within it. Looking at Earth's timeline and asking whether we're first, we see our moment clearly. We see what we're part of. We see what we're leaving behind. And that seeing, that perspective, might be exactly what we need. Not to answer whether ancient civilizations existed, but to understand what it means that we exist now. In the end, whether or not we're Earth's first civilization, we're certainly Earth's current one. And that responsibility belongs entirely to us.